All right, we're back for another episode of Connie 352. Today we're going to be discussing plumbing. Specifically, we're going to be talking about sewer pipes and sizing the sewer main. All right, to follow along at home, please grab the plumbing handout that I gave you. Now, word of note, a couple things I want to say about the plumbing handout. It comes from the textbook that I used, but since the bookstore updated to a newer version, and since that book wasn't all that great to begin with, the newer version actually got worse. So I haven't found a new textbook that I really want to use yet. So in light of that, what I've done is I've copied some of the pages out of there, and the real important part of these pages is not the text so much as it is the tables. For plumbing, I want you to think of this as it's for our class, this is going to be the code book. This is going to be what you use to size the number of fixtures, to size the mains that go out to the city connection. So this is our code book for the class, and it's really just the tables. Now, there's a couple other things in there that are helpful. A few of the things about some of the terms and that type of thing. But by and large, the important part of this is the tables. And since I made copies of this, I put the tables from the book in the order that you need them. One thing that always frustrated me about that book is that they gave you these tables kind of in the reverse order that you needed them. So if you look at the page numbers, you'll notice that the page numbers aren't sequential. And in fact, it kind of goes backwards. So just keep that in mind, that I put the tables in the order that you need them. Also, some of the stuff at the start, where it shows you a picture of a reverse osmosis system, some of the terms and stuff. I mean, we've gone over a lot of these in that first introduction one. So what I want you to do is let's just follow along here. I'll point some things out and let you take a closer look, and we'll get to the important part, which is the tables. So check out down here on the very first page of the handout, there's commonly used conversions. One of the most important ones in here, if you go down about halfway where it says 1 psi equals 2.31 feet of water column. Feet of water column, or inches of water column, is a way for us, just another way to express pressure. And when we get to the discussion about, well, how much pressure do we need at a city main to make the water distribution system work, we'll need that conversion later. So just know that that's probably the most important one on there. If you go down to the last one on that page where it says 1 drainage fixture unit is approximately equal to 1/2 of a GPM at drainage flow rate, get rid of that. Absolutely positively erase that. Cross it off, whatever. Please do not ever use it. Also, the one above it, water supply fixture unit is about 1 to 1.5 GPM. Cross that out too. There's tables that we're going to use for that. Do not use those shortcuts. So cross those last two conversions off. All right, from there, let's keep going. The next picture is something that we've already discussed. It kind of explains in black and white why a plumbing vent is necessary, but we've already talked about that. The next few pages are pictures of various water closets, the wall-mounted flush valve type versus the floor-mounted tank type. We've already discussed that. Right, here's a pressure tank, and we've already discussed that. There on page 239, see where it says low water use fixtures? Right, and it talks about the Energy Policy Act, which gives us the maximum amount of gallons per flush. Notice water closets, like we discussed on the last video, are 1.6 gallons per flush. That's the max allowed by code. Urinals are 1 gallon per flush. Lavatories are 2 gallons per minute, so that's a flow rate, and showers are 2.2. Notice it is possible to have significantly less water consumption. That's where we get those low flow fixtures. Here's a waterless urinal, that cartridge kind of a cut section. We looked at that last time. We also talked about the pressure tank, which can actually use the pressure of the fluid itself to force the water through it. Those are all options that we talked about last time. But let's get to the heart of it. How do we determine the quantity of toilets that we need, and then how does that convert to both the domestic water, the potable water supply size, and then the sanitary sewer size as it leaves the building? Notice there on page 244, we're going to talk about these occupancy numbers in a second, but the following are a definition, all right, some common terms that we're going to need for this class and that you should probably know for industry. All right, waste and sanitary waste are different things. Waste would be like the outlet of a laboratory, somewhere where you wash your hands. It's liquid water, right? Mostly water, maybe a little bit of soap, maybe a little bit of dirt from washing your hands, but it's not sanitary waste. Sanitary waste is discharged from plumbing fixtures like urinals, like water closets. All right. Soil waste is liquid discharge that potentially contains fecal matter. And that's why you hear the term soil pipe or a waste pipe. Sometimes people hear the term soil pipe and they don't understand, they think it's like a drain pipe or something, and it is not. A soil pipe is a waste pipe, is a sewer pipe. They are all kind of interchangeable, and sometimes people use those terms maybe where they shouldn't, and that's why I want to point out these terms below here. The difference: a sanitary drain is sanitary drainage system within the building. Once it leaves the building, it is now a sanitary sewer. It's the extension of the drain at the exterior of a building and connects to the city or public sewer system or to a sewage disposal system. See the difference? There's a drain within the building, and then a sewer is exterior to the building. Same way with stormwater. Stormwater is rainwater collected from the roof drains in exterior areas like parking lots. A storm drain is the main drain within the building, and then the storm sewer is on the exterior of the building that only contains storm water. Storm sewer and sanitary sewers are different things. Storm sewers can only have rainwater, and they can discharge to grade or to a stream or something along those lines. Sanitary sewer has waste in it, needs to go to a sewage disposal system. In rare cases, you may still see older cities using a combination sewer, a sewer that contains sanitary waste and stormwater. The history of this goes back to cities along the ocean. All of the rainwater went to the ocean, and originally so did all the sewer discharges, went straight to the ocean without going to a wastewater treatment plant. So they would have one pipe going from building all the way to the ocean. In rare cases, you might still see a combination sewer, but rare, and probably only along the eastern coastal part of the United States or maybe other countries. The problem with a combination sewer is that in times of high rain and flooding, all the sewers could also overflow, and sometimes that would result in them backing up into people's houses, and you get raw sewage coming out of drains, and just a bad idea. All right, so most of the time, storm sewer and sanitary sewer are different pipes going to different areas. All right, take a look at table 8.8. If you don't know the occupant number in a building, this gives you some rough rules of thumb to use about number of people per net free area of the building. All right. Assembly. If you have an assembly type of occupancy and it's got fixed seats in it, use the number of fixed seats. If you don't know that, right, then there's so many square feet per occupant. So like if there are movable chairs and tables in an assembly type of occupancy, you'd have 15 square feet per person. Business areas are 100 square feet. Now, notice, the actual occupancy might not be that dense. A lot of times, like in a business area, an office space, might be more like 150 square feet per person, something along that lines. This is for calculating plumbing fixtures, so don't get too caught up on how many people. Most of the time, a mechanical engineer will not go through this exercise. In other words, the architect is responsible for setting building occupancy, and usually they will tell you how many occupants are going to be in the building, and then you use that. There's no point in calculating the number of water closets for a building different than what the maximum occupancy is by code anyway. So just know that most of the time you just get this information from the architect. But for our class, like for your final project, I want you to use these numbers. So first, you find the number of people in the building on table 8.8. Next, go to the minimum plumbing fixture requirement here in table 8.7. See how I'm working backwards? All right, it just makes better sense this way. This gives you the number of occupants per water closet. Now, let's look at, and it varies. It's different for a theater, a church, and a stadium versus a restaurant versus an office or a school. All right, so just know that it's different based on the occupancy. Let's just pick one here, and I'm going to use theaters, right? Theater or church. What this is saying is for the first fixture, you can have one fixture per 50 people, but only for the first one. As soon as you go to 51 people, you need a second fixture. And then what it's saying is the next additional fixture can handle 150 more people. And then after that, it's 150 everyone after that. So notice, if I have 1 to 50 people, and notice this is split up male and female occupants. I'm going to talk about that one in just a second. But once you know the number of people, you say, all right, the first fixture can handle 50, and every additional fixture is another 150 people. So as soon as I have 201 people, I need a third water closet, and it goes up by 150 after that. All right, notice how different it is for, say, offices. The first fixture is for 15, and I don't know why they stopped, printing both of these, but it should be the same ratio, men and women. So the first fixture covers the first 15 people, and then every 25 people after that, you need another water closet. All right. Why is it different based on occupancy? Think of a theater or a church. Most of the time, events in a theater or in a church are limited to an hour, maybe 2 hours. In other words, I go to the assembly area for an event. When the event is over, everybody leaves. They are not in there all day like a business is, or a school like an elementary school where people are there all day. All right. So the ratio of water closets per person is different based on what the people are doing. Also, you do this calculation for men, and then you do this calculation for women. You have to divide them out first, and then do the 1 to 50 for the first 50, and then 150 each additional one. So then you do that after that. You do this for male, and you do this for female occupants. Always, unless you have an extenuating circumstance, you always assume a 50-50 split, male occupants and female occupants. All right, let me give you an example. Some people might make the argument that, well, what about Iowa State College of Engineering? Should we know that the number of occupants are going to be different as of right now based on enrollment. All right, the number of men versus number of women is different. However, that's still not an excuse to change it, because just know that those ratios, they are changing slowly over time. And obviously, look at town. We remodel town engineering about once every 50-ish years, hopefully, maybe 60. So we got to account for the future. So unless you have a compelling reason, it's 50-50. Let me give you some examples of buildings where there's a compelling reason that's been accepted by the local authorities. The United States Marine Corps, when designing a Marine Corps building, they know historically what the ratio of men to women is in the Marine Corps, and they know that it's not changing in the foreseeable future. Probably never. So they will tell you what that ratio is. Another example, I designed a building for the Boy Scouts, and their whole point was, we're the Boy Scouts. Yes, we want a few female bathrooms, but by and large, this is an association based on gender. It's the Boy Scouts. So they made a case, and it was accepted by the local plumbing inspector, that they wanted a different number of occupants, male versus female. Now, something important to know about this list. This is not code, but it's kind of close. This page kind of takes both the Uniform Plumbing Code and the International Plumbing Code and kind of blends it together. Do not use this if you ever have to design a building for real. Use the actual building code, but this is pretty close. And by using this, you don't have to buy a code book for me. So let's just use this. Notice there is note A down below here. One urinal may be installed in lieu of one water closet in male toilets for up to half of the required water closets. Up to half. So if we needed 4 water closets in a bathroom, and it's a male bathroom, we could substitute 2 of those as urinals. Right now, what if there was 3? Well, you can go up to half, so you could only substitute 1 urinal for 1 water closet. All right, so do the calculation, get the total number of water closets for men, total number of water closets for women, and then let's go to the next page. All right, let's take a look at, we're going to need to calculate drainage fixture units and water fixture units. All right. Now, if we were in class, this is the point at which I'd ask some of the mechanical engineers in class. I would say, hey, what's a drainage fixture unit? And what's a water fixture unit? And I'd ask them, what the conversion is between that and gallons per minute. And then, they'd look at me with this puzzled look on their face because they've never heard of a drainage fixture unit or a water fixture unit. And that's okay because it's a trap. Of course they haven't heard of it. All right. This is not the type of thing that they're going to calculate in fluid flow or heat and mass transfer. A drainage fixture unit and a water supply fixture unit, those are magical, mythical, nonsensical units that we use to size pipe in plumbing systems. They're not real units, okay? They are just, what they do is they allow us to take some kind of time-weighted average of water consumption in a building and use that to size our sanitary sewer main and our domestic water main. When I mean they're averages, in other words, you can't just take the peak flow rate for all the different fixtures and add them up. That won't make any sense. You will end up with a sewer main and a water main just far too large. And the truth is, not all of the water closets flush at one time. So there's got to be some diversity there to account for that rate of use part. And that's where drainage fixture units and water supply fixture units come in. They help the designer calculate what the average flow rates are going to be and try to size it based on a maximum that's going to go through them. So let's just take a look at these units. And today we're just going to be talking about drainage fixture units. All right, so let's take a look at drainage fixture units. First off, in this table, table 8.6, in this class, we are only going to be looking at the top half of this. Public or general use. Cross off the bottom half of this so you do not get confused. We are not going to be looking at private usage, water closets and showers and bathtubs and everything. So cross that off, the bottom half. Only look at the top. Next, there's different types here. There's water closets that are flushometer, which is a flush valve, water closet that is a gravity tank, and water closet that is a pressure tank. The pressure tank is the one that we were looking at, that is the pressure assist. Predominantly, unless it says otherwise, for a commercial building, you're going to be using flush valve water closets. So for this class, that's the only one that I want us to look at. Flush valve water closets. Each of those has a drainage fixture unit. See that first column? Drainage fixture unit of 6. So for every water closet, we'd add up all of those for the building and assign 6 drainage fixture units each and multiply that out. And we do the same thing for urinals, and we're going to use the flushometer ones. You might be kind of confused there. It's like, see where it says urinal tank type? Maybe you've never even seen a tank type urinal. In all honesty, I've only seen them once in my career, and that was before they remodeled the Memorial Union when I was a student in like 1995. They actually had urinals with these huge tanks up above on the wall up above the urinal. And they were the last ones I've ever seen. So they do exist, but if we're designing from new, we're not going to use them. Okay? So urinals are 4 drainage fixture units each. Lavatories are 1, so on and so forth. You'll be able to look through there. So what you do is you take the drainage fixture units for each type of fixture, multiply that out, and get a total drainage fixture unit for the entire building. All right. Then, okay, now I'm going to skip the next few pages. We're going to come back to this. When we use the second half of table 8.6 and we look at water supply fixture units, that's when we're going to come back to these next few pages. But we're going to go to the end, right? And we are going to look at table 8.10, where it shows us the maximum number of drainage fixture units connected to branches and stacks. All right, this is the table. Hold on a second. Oh, hold on a second. Look at table 8.11. Table 8.11. All right. Table 8.11, not table 8.10. The maximum number of fixture units that may be connected to a building drain or building sewer. I don't want you looking at the horizontal one or the table 8.10 because it differentiates it between stacks, which are vertical, and horizontal branches. I want you looking at table 8.11, which gives you the pipe diameter, and that's along the left. And then you also have to look along the top, which is pipe slope. Pipe slope. In other words, the force that gets the water and the sewage through a sewer pipe is slope. In other words, this is gravity drain piping. If there's water in there, it should be moving, and it's moving because that pipe is forever tilted downward away from the building. Or, I'm sorry, away from the fixture, out of the building and towards the city sewer. All right. Notice that it changes the amount of fixture units that can be connected to a building drain or sewer varies depending on pipe slope. First off, I want you to take that 1/16 of an inch per foot column and erase it, or rather cross it out. Don't use it. I cannot imagine installing sewer pipes at an 1/16 of an inch per foot. That is not going to happen. So don't do it. Next, 1/8 of an inch is usually the minimum that you're going to start at. 1/8 of an inch per foot. And that's only for sewers 4 inches and above. But in all honesty, for a building main drain, there's no point in making one less than 4 inches because most toilet outlets are also 4 inches. Just as a friendly piece of advice, do not size a sanitary drain pipe from a toilet at less than 4 inches. So at an 1/8 of an inch per foot, 4-inch pipe can handle up to, the way this table reads is it can handle up to 180 drainage fixture units. As soon as you go over that, you have to go to a 6-inch pipe. Now, if you increase the slope of that pipe, that 4-inch sewer main can handle 216 drainage fixture units if it's sloped at 1/4 of an inch per foot, and then it can handle up to 250 drainage fixture units if it's at 1/2 of an inch per foot. 1/2 of an inch per foot of sewer pipe slope will get you very deep in a hurry, right? So that'll end up being a deep pipe in a hurry. So that is rarely done. But it can happen in rare cases if you really, really needed, really wanted to avoid going up a pipe size. All right. So the progression: find the occupancy, determine the number of fixtures, multiply the number of fixtures by the drainage fixture units each, add them up for your building, and then use table 8.11 to size the sewer main. All right, so what I've done here is I've pulled up a picture of this is just a residence, but it would apply for commercial buildings as well. You know, it just kind of illustrates here at the edge of the building, the sewer leaves the building, goes over to the property line, and then eventually connects to the sewer main. Now, the steeper the slope that you get on this pipe, the smaller the pipe could potentially be. But also notice something else, that if the further back from the property line the building is, or the deeper a basement or something along those lines might end up being, the deeper that is, the greater the chance that you're going to have to make that pipe flatter and flatter. In other words, less and less slope just to be able to meet this connection here at the street. Now, something important, you can have a building further away than the slope would allow you to get to the sewer main. You can have a basement deeper than the sewer main connection. But if either of those things are true, then you're going to have to install something called a lift station. A lift station, here, this is just a cutaway of a lift station. All a lift station does is the sewage water comes in, it is pumped up to a higher level, and then it gravity drains from there down. You might see lift stations on properties, but you also might see large lift stations across cities. I mean, it would make sense, right? Because we can't just keep going as the city gets bigger and bigger and bigger. It's not possible to only build on higher and higher elevations so everything flows to the sanitary sewer treatment facility. So periodically within a system or within a city, you're going to have a lift station that takes that sewage and lifts it up so that it can continue in a gravity drain type of a format. However, a couple of important caveats here is that lift stations are powered by pumps, and pumps break. Pumps get clogged. Pumps need maintenance. All of those things. So just bear in mind that with pumps comes maintenance issues. Also, kind of a current events type of a thing. Current events, because of the toilet paper shortage, people are using wipes and t-shirts with predictable results. This just happened 3 days ago. This was just published 3 days ago. This is the Houston Chronicle. This is a picture of everything from paper towels, tissue paper, allegedly flushable wipes. Flushable wipes aren't. They're not flushable. Don't do it. Flushable wipes, t-shirts. Man, I think that even looks like a bounce dryer sheet. I don't even know what to think of some of this stuff. These are all things in a screen. This is a single screen at the district's pumping station. This is one screen. Now, apparently, this is after they were washed. Don't ask me why they were washed. I have no idea. All right. But someone had to go into this pumping station, remove all this stuff out of there, and clean it out. And if you want to look, right, just Google lift station clogs or lift station flushable lift station problems. And you will find tons of pictures of things that are stuck inside of a lift station that should never have been there. So for current events, please only flush toilet paper, and everything else needs to go into the trash. All right. Otherwise, somebody's got to get down in those lift stations and clean them out. Yeah, there. This is the inlet to a pump. And this is somebody trying to pull out all the stuff that's clogged it up, right? So is this. I mean, picture after picture after picture, right? Here's a guy trying to get to a lift station in Florida. That doesn't look like fun. If you want to watch a good episode of Dirty Jobs, find the episode where the Dirty Jobs crew follows somebody who cleans out lift stations. It's lovely. Just a great episode. Anyway, all right. So I'm also going to post here probably Monday, by the time you get this video. I'll also post one of the homeworks for you to take a look at as well, to give you some experience on how to use those tables. So let me know if you've got questions. Let me know if you got comments. Let me know, how the class is going. Be sure to ask if you've got final project questions, and I can set up a time for a WebEx meeting or FaceTime meeting and answer some of your questions that way. Be sure that you're keeping up on the discussion boards and following along on the video lectures. All right, that's all for sanitary sewer piping, and I will see you next time for domestic water service piping sizing.